This is a new topic, circle geometry. So we're just looking at terminology. We know what a circle is. It's a set of points, fixed distance from the center. A semicircle is just half the circle, okay? A chord is a straight line segment joining 2 points on the circle. For example, here we will say chord AB. So AB is a chord, but a chord, if I jump down to number 5, that passes through the center of the circle, the diameter is also a chord. It's a special chord that passes through the center. You all know radius from the center of the circle to a point on the outside of the circle. Secant, it's like a chord, but it's a line. It's not a segment. So remember, a segment has a fixed, or an interval has a fixed distance, whereas a line has arrows on the end and goes on forever. That's a secant. Okay, it cuts the circle in 2 points. AB is a secant, so it goes beyond the circle. An arc, we know, is part of a circle, and we know what a sector is. It's part of the shaded area bound between 2 radii and an arc. Okay, now there's one more that's actually not there that I'm going to add. Actually, no need to add it. It's over the page. We've got segment. So it's the area bound between the chord and the arc, and part of the by an arc. This is called the minor segment. So whenever you have a chord and you shade in the areas on either side of the chord, you'll have a minor segment, which is the smaller segment, and the major segment of the circle. Okay. Concentric circles are circles that have the same center but different radii. Okay, this is just AB is, so a straight line perpendicular to AB through the midpoint of AB, that's called the perpendicular bisector. So you might want to write that over there. So the perpendicular bisector, it bisects your interval at right angles. So perpendicular bisector, it's a straight line perpendicular to AB through the midpoint of AB. Collinear points are points that lie on the same straight line, that lie on a straight line. Non-collinear points are points that do not lie on the same straight line. Of course, you could join up any 2 points, but you can't get a 3rd or 4th point on the line. And a tangent is a straight line that touches the circle at 1 point only. Okay, and we know the circumference is pi d, or the circumference is 2 pi r. Now, last one, this is an angle at the circumference. So naming those, that's an angle at the circumference, because the angle is touching the circumference. Okay, this is, if this is an angle at the circumference, what do you think this second one is? An angle at the center. Yeah. This is called an angle at the center. And what's this last one? You should know that one. And that's an exterior angle. Okay, so we're going to be using all this terminology. Angle at the circumference, angle at the center, the exterior angle. Here's a new word, subtend. So the word subtend means to extend under or to be opposite to. So if we look at this diagram here, the arc AB. So the arc is along the circle. So the arc AB is that. The arc AB extends under angle AOB. So what we say is the arc AB subtends angle AOB. That's what that means. Basically that the angle from the endpoints of that arc, that angle is formed from the endpoints. So we say that the arc AB subtends angle, that's angle symbol, AOB. We can also say it about the chord. So when you're going from A to B, you can go along the arc AB, or you can do the chord AB. So if you've ever got to mention AB in one of your proofs, or one of your proofs, you need to say whether it's the chord AB or the arc AB. Okay, you can't just say AB anymore. The chord AB also extends under the angle AOB. So we say that the chord AB subtends angle AOB. Okay. Now, we could also say that if we want to say this in reverse or converse, you would say the angle at the center, in other words, angle AOB is subtended by arc AB. So I can say arc AB subtends angle AOB, or I can say angle AOB is subtended by arc AB. I can also say the same about the chord. The angle at the center, angle AOB, is subtended by chord AB. So the arc or the chord subtends the angle, or the angle is subtended by the arc or chord. Okay, now. Okay, so angle ABC. So this angle is subtended by what? By chord. I'm just going to by AC, because I don't know if if it was in a circle, it'd be a chord. Okay, chord BC subtends which angle? Angle BAC. Okay, angle ACB is subtended by, yeah, but I'll just put AB because I don't know if it's a chord or whatever. And chord AC subtends which angle? Yeah, CBA or ABC. Do we get that? So chord AC, oh, we'll call them chords. They're calling them chord. I'll call them chord. So chord AC subtends angle ABC. So we're going to do some examples down here where we use the term subtend to describe the relationship between angles, chords, and arcs in these diagrams down here. So we're using the term subtend to describe the relationship between angles, chords, and arcs. Okay, let's go. Is this angle going to be subtended by a chord or an arc? Can you see a chord or an arc here? So angle is subtended by arc CB, or I can say arc CB or BC subtends angle, arc CB subtends angle CAB. Okay. A just happens to be the center of the circle here. Oh, no, that's just a marker. Okay. And I could say here that the angle at the center, which is angle CAB, is subtended by that arc, or arc AB subtends angle CAB at the center. All right, the next one. Angle what? Your DCB or BCD is subtended by what? By chord or arc. I'm going to go chord BD. You could also use arc. It could be either. And chord BD subtends angle BCD. Is this one at the circumference or at the center? Yeah.
Do you have to write both? You can just choose.
You can write just one of them. One of them's fine. So this one's at the circumference. So chord BD subtends angle BCD at the circumference. And I could say here the angle at the circumference, which is angle BCD, is subtended by chord BD. The A is just the center of the circle. Yeah. See, because this angle is subtended at the center of the circle and the other one is subtended at the circumference. Now that's going to be really important with a number of our theorems, that you specify whether it's angle at the center, angle at the circumference. Geometry theorem. So circle theorem 1, and we're going to prove these as well. But just watching here, at the moment you can see that both the arc lengths are 3.1 and the angle in the middle, the angle subtended at the center by those arcs is 55.9 degrees. Now if I change the size of the arc, so now that the arc is 5.5, the angle in the middle is roughly 90. So this makes sense, because what is the formula for arc length? Isn't it theta over 360 times 2 pi r? Remember? Formula for arc length is theta over 360 times 2 pi r. So if the angle at the center is the same, then you would have the same arc lengths. So this is our first theorem. So if I go back to 3.1, I mean, remember there is a bit of rounding, so I'm trying to get it exactly the same. Okay, So there is circle theorem number 1. So put that in the space, circle theorem 1. Equal arcs subtend equal angles at the center of the circle. Here we go. So circle theorem 1, equal arcs subtend equal angles at the center of the circle. And the converse theorem is if two arcs, so we're sort of saying the reverse. So in the first one, we're saying if the arcs are equal in length, then the angles at the center are equal. And the converse theorem is if two arcs subtend equal angles at the center. So the second one is saying if the angles at the center are equal, then the length of the arcs are equal. Okay, so that's the converse theorem. So if two arcs subtend equal angles at the center, equal angles at the center of the circle, then the arcs are equal. So put that in the space that says converse. I'll just fix this in a minute. So your sheet should look like this at the moment with circle theorem number 1 and its converse. Similar to theorem number 1, instead of talking about arcs, we talk about chords. Okay, so at the moment these chords are not equal in length. So let me make the chords equal in length just by, there we go. So when the chords are equal in length, so equal chords subtend equal angles at the center, that is the theorem, circle theorem number 2. And the converse is that equal angles subtended at the center of the circle cut off equal chords. Okay, so just writing that in. As you can see, if I change the length of the chord, the angle at the center is different. Okay, remember there's some rounding here, so I sort of have to get it the same. So they're the same within, you know, with rounding. Like this, circle theorem 2. Okay, equal chords subtend equal angles. So if the chords are equal, then the angle at the center is equal. And the converse is if the angles at the center are equal, they cut off equal chords. Okay, to your student notes work booklet. Student notes booklet. Okay, just going to the second page. See if you can write those. Can you write those theorems again for practice? So I want the theorem and its converse, circle theorem 1 and its converse. Try and, if we'll try. And then circle theorem number 2 and its converse, write those in there. And then we're going to do some questions down the bottom.
Is it alright if I do?
With the first one, equal arcs subtend equal angles at the center of the circle, or if two arcs subtend equal angles at the center of the circle, then the arcs are equal. But the converse of this one could also be if two chords subtend equal angles at the center of the circle, then the chords are equal. So you don't have to word it exactly like this, but you just need to say, well, if the angles are equal, then the chords are equal. And in the other theorem, if the chords are equal, then the angles are equal, basically. So equal angles subtended at the center of the circle, cut off equal. So it just showing you a different way of saying it. Cut off equal chords. So you could do the converse in either way. The way it's written in 1 or 2, just exchanging, replacing chord and arc, you know, with each other. Arcs subtend equal angles at the center of the circle. Now we know that the arc length is L equals theta over 360 times 2 pi r. Okay? Now we know that, so therefore L1 is theta 1 over 360 times 2 pi r. And we know that L2, the chord length of chord of arc L2 is theta 2 over 360 times 2 pi r. But we know that L1 equals L2 because the theorem is equal arcs subtend equal angles at the center of the circle. So if L1 equals L2, I can say, well, theta 1 over 360 times 2 pi r equals theta 2 over 360 times 2 pi r. We okay with this? So remember, the theorem is equal arcs subtend equal angles at the center. So we're just writing an expression for the length of arc L1 and the length of arc L2. But we know that L1 equals L2 because we're trying to prove that if the arcs are equal, the angle at the center is equal. So therefore, we put equation 1 equal to equation 2. sub 1 into 2 or 2 into 1, whatever, and we get theta 1 over 360 equals that. Now, you can see you can divide both, you can divide through by 2 pi r and multiply through by 360. You will get, therefore, theta 1 equals theta 2. So we've proven the theorem. Because, look, the 360s are the same and the 2 pi r's are the same. So, therefore, we've proven the theorem. Arcs subtend equal angles at the center of the circle. So I know we've written it out, and the converse is also true. Equal angles subtend equal arcs. Equal angles at the center subtend equal arcs.
So that's like your proof.
Yeah, that's my proof of that theorem. Okay? And the converse is also true. I'm not going to prove the converse. The converse is also true. So if you were proving the converse, you'd say, well, I know that theta 1 equals theta 2, and then you're proving that L1 equals L2. That's proving the converse, that if the angles at the center are equal, the arcs are equal. You'd use the same formula, but you just say, I know theta 1 equals theta 2, therefore L1 will equal L2. 2 is equal chords cut off equal angles or subtend equal angles at the center of the circle. So let's start with our, so I've got my center of circle O. I'm calling this chord AB chord CD. I know that the chords are equal in length. So I'm trying to prove that equal chords subtend equal angles at the center. So I go in triangle AOB and triangle AOB and triangle COD. What do we know? We know that AB equals CD, that's given. So we're given that AB equals CD because they're equal chords, right? We're trying to prove that the angles at the center are equal. Now what else do we know? Radii. So OA equals OC, it doesn't matter which way you do it. So this is what else we know, that OA equals OC and OB equals OD. Well, they're all equal to each other. So OA equals OC and OB equals OD equal radii. And similarly, may as well write equal radii as well. So therefore, triangle AOB is congruent to triangle COD by what? I've marked them all. SSS. And so therefore, what would I do now to show that the angles at the center are equal? What would I do? Therefore, angle AOB is equal to angle COD. Reason, corresponding or matching angles, corresponding angles of congruent triangles. Okay, so that is the proof. So let's just write, therefore, equal chords subtend equal angles at the center of the circle. Now, if you want to prove the converse, it'd be not the SSS proof. Do you know what proof it would be? If you want to prove the converse, if I was to prove the converse, I'm not going to do the full proof, but we're just going to write a little bit about it. What if the angles are equal at the center? So let's say the angles are equal and you know that you've got equal radii. You would also, so to prove the converse, you would use SAS. Do you get it? So to prove the converse, you would use SAS. And then, do you get it? Because the angle at the center is equal radii, SAS, and then you would have matching sides or corresponding sides of congruent triangles. And then AB equals CD by corresponding sides of congruent triangles. but you don't have to do that proof. All right, just showing how you would prove the converse theorem. Okay, back to the student booklet, the one that says student booklet. Here we go. So these are very easy. We start off with fairly easy ones, but you just have to practice whether you're using the theorem or the converse theorem. So find the value of the pronumerals giving reasons. So what's equal here? The arcs are equal. So you would say beta equals 32 degrees, reason. Practicing the theorems. What's the theorem? Equal arcs subtend equal angles at the center of the circle. That's that theorem. So sometimes you're going to use converse. All right, so beta would be 32. What about this one? Is this the converse theorem? So this one would be that x is 6. Why? Because, yeah, you could say equal angles subtended at the center, cut off equal arcs, or you can say if two arcs subtend equal angles at the center of the circle, then the arcs are equal. This is the converse theorem. So I've got if two arcs, you can either use either of the converses, subtend equal angles at the center, then the arcs are equal. So that's the converse theorem, this one. See, that one's written as the converse. So can you see how you use the normal theorem and the converse theorem? Now, AB is a diameter of the circle, and we know that arc CB, so I'm going to mark it, equals arc BD. You have to prove that angle AOC is equal to angle AOD. So you're trying to prove that this angle here equals that one there. Okay. Angle COB equals angle DOB. Why? I'm going to call them equals theta, I'm going. So equal arcs subtend equal angles. Now remember, you can use the angle symbol at the center of the circle. What we really should say is let theta equal angle COB first, right? So angle COB equals angle DOB equals theta, equal arcs subtend equal angles at the center of the circle. So angle AOC is, let's write, what isn't it, 180 minus angle COB, which is 180 minus theta. Why am I writing that? And you'll do the same for angle AOD, is 180 minus angle DOB. Now you need to state that because there's more than one theta now, which is 180 minus theta. Reason? You can do supplementary angles, angle sum on a straight line. What do you want to do? Angles on a straight line. I'd be saying which straight line it is. Angles on straight line AOB. You call that straight line AOB, not AB, AOB. And similarly, or you could use supplementary angles. So whenever you're mentioning a straight line angle, you need the vertex, which is O. AOB is the straight line, because it's like an angle, 180 degree one. All right, so therefore angle AOC equals angle AOD. Because they're both equal to 180 minus theta, you don't need to mention that, it's obvious. Down here, given that chord AB is equal to 3.2 meters and angle AOB equals angle COD, what is the length of DC? Well, you know what the length of DC is. So DC equals, it's just practicing writing the theorem. You're not going to get anything as easy as this, but it's just practicing the theorem. Is this the theorem or the converse theorem? Okay, so the converse is if two chords or equal angles subtended at the center of the circle cut off equal chords. It's, or you can put, yeah, so look, basically you want to say equal angles at the center cut off or subtend, yeah, equal angles at the center, equal angles subtended at the center cut off equal chords, or you want to say if two chords subtend, the chord subtends the angle and the angle is subtended by the chord. Okay? So equal angles subtended at the center cut off equal chords. So basically, what you're saying here is that the angles are equal, so the chords are equal. And the other way you were saying that the chords were equal, so the angles, the other way will be the chords are equal, so the angles are equal. So this one, given that AB equals CD and angle AOB is 30, find the value of angle COD. So angle COD is 30. Reason? Equal chords. So we've got the equal chords this time. Subtend equal angles at the center of the circle. Well, it's obviously a circle. Practicing the theorems, writing them out. Practicing the theorem and its converse, okay? AD is a diameter of the circle with center 0, O, not 0, O, where AB equals CD. So make sure you put that on. AB equals CD. Prove that BC is parallel to AD. Now remember, with parallel lines, you can prove them by corresponding, alternate, or co-interior. Okay, so what do we want to say first? We know that AB equals CD. So what do you think you'll do first? No, let's just use our theorem. So if AB equals CD, doesn't it mean that what equals what? Yeah, so let's do that. So angle AOB is equal to angle DOC. So you don't need to prove the theorem and you don't need to prove congruence. Reason? Equal chords. I'm going to go AB and CD in brackets. Subtend equal angles at the center of the circle. Now that we know, so what I'm going to have to do to prove parallel, I've got to prove that these base angles are theta, don't I really? If I can prove that these are theta, I can do alternate. So what am I going to do here? Can I find the size of this one? How do I find, what sort of triangle is BOC? Isosceles. Do you think you could find the size of this angle up the top? At the apex of the triangle? So angle BOC is what? 180 minus 2 theta. Why? Angle sum of, no, you only use supplementary if it's only two angles. So angle sum of straight line. The straight line is AOB. Now, so I'm going to put 180 minus 2 theta in here. So now we can say that OB equals OC equal radii. Why am I doing that? So therefore triangle, thank you, no, OB equals, oh, BOD. Oh, AOD, thank you. Okay, so OB equals OC, so therefore triangle BOC is isosceles. I'm just saying that the triangle is isosceles. I'm going to put those, and so now I can work out the size of, therefore, angle OBC, angle OBC, how would you work it out? 180 minus, I'm going to go, so therefore, sorry, angle OCB equals angle OBC. Do you know, I'm trying to say that those base angles are equal. Equals 180 minus 2 theta over 2. Did you get that? Why am I saying that? what's the reason for this 180 minus business? Angle, sum of triangle OBC. I could see three triangles there. So I need to say which triangle. So these are theta. Great. So therefore, I can prove that the lines are parallel. So therefore, AD is parallel to BC. Oh, reason, the alternate angles, angle AOC is equal to angle OBC equals theta. Alternate angles are equal. AOB is alternate to OBC. Oh, AOB. So alternate angles. So they're parallel because the alternate angles AOB and angle OBC are equal. Or we can say angle AOB is alternate to angle OBC and they're also equal. Theorems and their converse. Okay?